Okay, so in this video we're going to start talking about electric circuits. This unit over circuits is going to include topic 5.2 and 5.3, and so we're going to start with 5.2, which is technically called heating effect of electric circuit, or electric currents, but it's really mainly about circuits. Alright, so some of the things you need to understand in 5.2, how to draw and interpret circuit diagrams, Kirchhoff's circuit laws. That's probably the main part of this unit. Heating effect of current and its consequences. Resistance expressed as R equals V over I. Okay, that is actually a definition that you need to make sure that you know. Ohm's law and the idea of Ohm's law. Resistivity and power dissipation. The things you must be able to do. You must be able to draw and interpret circuit diagrams, identify ohmic and non-ohmic conductors through a consideration of the VI characteristic graph. That's very easy to do. Solving problems involving potential difference, current, charge, Kirchhoff's circuit laws, power, resistivity, and resistance. That's probably going to be the most difficult part of this unit. These problems can range from very, very easy to very, very difficult. Investigating combinations of resistors in parallel and series circuits, describing ideal and non-ideal ammeters and voltmeters, that's also very easy to do, and describing practical uses of potential divider circuits, including the advantages of a potential divider over a series resistor in controlling a simple circuit. And that's probably one of the last things we'll talk about in this unit. Okay. There are a number of equations given to you in the data booklet under 5.2. Kirchhoff's circuit laws are both given to you. This is the way they're given to you in the data booklet. We'll talk about these as we go through the unit. This equation right here basically defines electric resistance. There's three equations for power dissipation that we'll talk about. And then we have two equations for what's called the total resistance or equivalent resistance for series and parallel circuits. We'll talk about those when it comes up. And then this last equation here is for what's called resistivity, not to be confused with resistance. Okay, but we will talk about all of those things in time. Something that's not in 5.2, it's technically in 5.1, is also the drift loss equation that is in 5.1. It is technically part of 5.1, as is the definition of current. Both of those equations are given to you in 5.1, but we will talk about them here in this video to start off with. Okay, and we've already talked about current before, but just because it's such a central part of this unit, let's review. So we've talked about electric charge and electric fields before, and basically to sum up, if you have charged particles in an electric field, then they will accelerate in the presence of that electric field. Okay, if you put a charged particle in an electric field, it experiences an electric force, the Coulomb force, etc., etc. And so if you have moving charge, then you have current, okay, by definition. Now, electric current is defined as the rate at which charge flows past a point in 1 unit of time. And when I say 1 unit of time, that basically just means, t equals 1, whatever unit t has to be measured in. Seconds, minutes, hours, whatever. Obviously, in SI units, that would be in seconds. Okay, so if you think just in terms of SI units, current is basically how many Coulomb flows past a point in space per second. Okay. The SI unit of current is the ampere. It is named after a guy, which means that is given a capital A when you write it. And so 1 ampere is basically 1 Coulomb of charge flowing past 1 point in 1 second. The symbol for current is a capital I. It's sometimes written as a lowercase I, especially in electrical engineering. But we're primarily going to write current as a capital I, although I guess it doesn't really matter. And I do want to remind you that the ampere is one of the 7 SI base units, the 7 fundamental units that the SI unit system is built on. Now these next two examples, I believe we've already done these before, so I will just go through these really quickly. But based off of the definition of current, which is given in the data booklet, I believe as I equals delta Q, remember Q is charge, over delta T, you can see that current is the rate at which charge moves over time. And so a current of 12 amperes, that's I, flows through a wire in 1 minute. Okay, so here, delta T, or you could just write T, is 1 minute, which of course is 60 seconds. We're asked to calculate the amount of charge that flows past the point in the wire in this time. And so, of course, this is just like a really basic type of question. Here, delta Q would just be I times delta T. And so 12 amperes, that is 12 coulomb per second, times delta T, which is 60 seconds. That would be 720 coulomb, which is a massive amount of charge. Actually, 12 amperes is quite a lot of charge. But that's the answer to the first question. Now the second question says calculate the number of electrons that flow past this point during this time. Now you should remember from a couple of units ago that the charge of one electron, say Q electron, is negative 1 E, where E is the elementary charge. And so that would be negative 1.6 times 10 to the, I don't know why I put, times 10 to the negative 19 coulomb. So if we want to know how many electrons make up 720 coulomb, ignoring the negative sign, because, you know, the negative sign doesn't really do anything for us here. 720 coulomb. If we know each electron has a magnitude of charge of 1.6 times 10 to the negative 19 coulomb. That's the charge of one electron. Again, the negative sign doesn't really do anything for us here because we can't have a negative number of electrons, obviously. And so it's just a simple matter of division. 720 divided by 1.6 times 10 to the negative 19. I get 4.5 times 10 to the 21 electrons, and that's the answer to the to the second question, which is quite a lot of electrons flowing in 1 minute. That's almost a mole of electrons. Okay, so just really basic understanding of what electric current is. Okay, that's how quickly charge flows. Pause there if you need to look at that. And then question 2, it says a large bolt of lightning carries a charge of 15 coulomb, which again is a massive amount of charge, from a thundercloud to the ground with an average current of 30 kiloamps. That is a massive amount of current right there. 30 kiloamps. That's 30,000 amperes. Wow. Calculate the time of the lightning strike. Again, this is just a really basic example. It's not really common to see problems involving the definition of current like this, but of course you need to know what current is to be able to talk about electric circuits. So if you just rearrange this equation for T, you get, charge over current. Okay, that's just kind of basic algebra. You get 15 divided by 30,000. So typing that into the calculator, 15 divided by 30,000, we get 5 times 10 to the negative 4 seconds. Okay, which is a very short amount of time, but that makes sense because it is a lightning strike. Okay, so pause there if you need to look at that some more. Okay, so now that we know what current is, this is just another slide with the definition of current. We're going to use an analogy throughout this unit where we kind of analogize electric circuits to water flowing through a pipe. Okay, and so if you imagine like a conductor as like a pipe that holds electrons, the moving electrons that constitute the electric current would be like water flowing through a pipe, and the faster the water flows, the faster the current. Just like in a wire, the faster the electrons flow, the faster the current. Okay, so now, by the way, if you want to know why is it that electrons are flowing rather than protons or neutrons, that's because if you think of the model of an atom, the electrons are on the outside of the atom, and so they're more easily transferable. I will say in the vast majority of cases that we're going to talk about, it is electrons, moving electrons that constitute the current. Okay, if you think like a copper wire, if you hook a battery up to a copper wire, that's the electrons flowing in the copper wire. There are situations in which the electrons are not the charge carriers. But in most situations, when we talk about current, we're actually talking about electrons flowing. Not 100% of the time, but most of the time. Okay, you could also have, for example, like ions flowing. If you apply an electric field to like an ionic solution or something like that. Okay, but most of the time, we're talking about electrons flowing. Okay, so electrons are the charge carrier. Now, in 1916, we figured this out, that when you're talking about a metal, the charge carriers in a metal are electrons. Now, remember that before like the 1900s, we didn't have any idea what the model of the atom looked like. Electrons were not even discovered until the late 1800s, like the 1890s, by J.J. Thomson. We've talked about him before. And so people started doing experiments with electric circuits, like, in the early 1800s. And so it wasn't until like almost 100 years later that we actually had an idea of what was going on. Okay, so it turns out the charge carriers in a metal are electrons. Okay, and if you think of what we now know about atoms, in the atom, or if you think of just like a bunch of atoms, you have a bunch of moving charge. You have the electrons spinning around the nuclei, and they're zooming all over the place. Technically speaking, that does constitute current, but that's not what we really think of when we talk about a current going through a wire. Okay, if you look at this slide, it says in a metal, free electrons move very rapidly, but collide constantly with the atoms in the crystalline lattice structure of the metal. Note that through any cross-section of the conductor, the net current is zero. Basically meaning if you have a bunch of electrons zooming all over the place, let's just say like you have a piece of metal sitting on the table, there are electrons, and they are moving very fast, but they're moving kind of randomly, and they're bouncing off of each other. And so each electron moving by itself might make up a small little current, but as a whole, a piece of metal sitting on the table doesn't have a current running through it, okay, unless you attach like a battery or something to it. Okay, so although the electrons have a very high velocity, the net result, because they're bouncing in random directions, the net result is that the electrons as a whole are not actually moving. Okay, each individual one might be moving, but as a whole, they're not. Now, let's say you take that piece of metal that's just sitting on your table in front of you. If it's not attached to anything, even though you have moving electrons, there's no net current in the metal. Okay, like we just talked about. But if you apply a potential difference to that metal, then basically what that means is if there's a potential difference, there is an electric field. We've talked about that before. And if there is an electric field acting on a piece of metal, that means the free electrons in that metal are going to feel an electric force. Okay, and so now we have the electrons moving in a different way. Not only are they moving around like randomly colliding with each other, but they're also kind of drifting from, I guess it would be from low potential to high potential, because that's how electrons work. Okay, now we have a net current, okay, because now all of the electrons are drifting as a whole rather than just kind of randomly moving along. And this speed of this net migration is what we call drift velocity. Okay, and so I will say drift velocity, you might see one or two problems about it. It's not typically a super important thing, but I do want to talk about it because it has been on the IB exam the last couple of years, and I want to make sure you understand the concept, even though it's not super complicated to do calculations with drift velocity. Okay, so here's a simulation to explain what I mean. What you can see is when I first go to the simulation, the electrons are kind of moving around kind of randomly. Okay, but if you apply an electric field, they all kind of move against the electric field. Okay, so in the first instance right here, we have random motion of electrons. Okay, that means there's no drift velocity. We just have a piece of metal sitting on the table. And then if we apply a potential difference, as you'll see in just a second, now the velocity at which these electrons are moving now, that's what's called the drift velocity. Okay, so no drift velocity here, just kind of randomly moving electrons bouncing off of each other, not in any particular direction. Now there's an electric field, now there is a drift velocity. Okay, so no drift velocity, You apply potential difference, now there's a drift velocity. Okay, so the drift velocity is basically how fast the electrons in the conductor are drifting when you apply any electric field. Okay, so right here, however fast they're moving is that drift velocity. Now, there is an equation which is given to you to let you calculate drift velocity, and we'll talk about it in just a second. But basically, the idea of the equation is, let's say you have the current I. That's how many coulomb are flowing past the point in a wire per second. Okay. Now, in a certain time, delta t, there's a certain volume of electrons that flow in a wire. So a wire is like a cylinder. Okay. So imagine the drift velocity is v. Okay, so you apply a potential difference to a conductor, the electrons begin to drift along the wire, and let's say that drift velocity is v. Okay, v times delta t represents how far those electrons travel in that amount of time. And if the area of the wire is a capital A, notice here this area is a circle. Okay, this is what we call the cross-sectional area, because the cross-section of the wire is a circle. Then V delta T times A represents the volume of the electrons that flow through a wire in the amount of time delta T. Okay, so V delta T times A is volume. Okay, because the volume of a cylinder is basically A times the height of the cylinder, and here the height is V delta T. Okay, so this is the volume of electrons that flow through a wire. If we know the number of electrons per unit volume, then we can use that to find the charge. The IB calls the number of electrons per unit volume, they call that N, a lowercase n. Okay, that's the free electrons per unit volume. I'm sure it probably has a name, I can't think of it off the top of my head, but it probably does have a name. Okay, so N is basically how many electrons you have per cubic meter, essentially. Okay, so in other words, if you take N, the number of electrons per unit volume, and you multiply by V, that is the volume that these electrons move through in a certain amount of time, that would represent the number of electrons. And if you know the number of electrons, then you can figure out the current, right? Because the current is delta Q over delta T. Okay, and we know that the charge of each electron is the elementary charge. Right, so the overall charge, delta Q, would basically be the number of electrons times the charge of one electron, which is E. And so if you put all this together, you end up with an equation for I. Okay, so I is delta Q over delta T. Okay, delta Q is the number of electrons times E, and the number of electrons is N times V, and V is V delta T times A. And so I know this seems kind of convoluted, and it really is, to be honest. Okay, so N V delta T A times E, all that is equal to the charge. And so if you divide by delta T, you get an equation for I, which I will write up here. And it looks something like this. And this is the drift velocity equation. And I said before that drift velocity is not a super important concept in this unit. It is something that you have to be able to do problems with it just in case it comes up, but it's not super important. But I want you to be able to recognize it when you see it. Okay, so what does this equation mean? Well, basically what you would do with this equation is it typically allows you to calculate the drift velocity. Okay, usually N is a given. Usually A, they don't give it to you directly, but they might give you like the radius or the diameter of the wire. And then E, of course, is the elementary charge, and I is the current. Okay, so pause it here. Make sure you have this in your notes. Okay, and this basically just has everything we just talked about filled in. This equation is given to you at the bottom of 5.1. And here in this slide you can see everything written out. Sometimes it says drift speed, sometimes it says drift velocity. It doesn't really matter. Okay, N again is the number of electrons per cubic meter. That's almost always given to you. I is the current in amperes. Drift velocity is given in meters per second. The elementary charge, you should know what that is, of course. And then the cross-sectional area is in square meters. Okay, keeping in mind that the shape is typically like a cylinder, and so A is pi r squared. Usually they give you the radius or the diameter, and you have to find A. Okay, so just to give you like a really basic example, suppose the current in a 2.5 millimeter diameter copper wire is 1.5 ampere, and there are 5.0 times 10 to the 26 free electrons per cubic meter. Find the drift velocity. Again, these equations, or these types of problems with drift velocities are not really complicated at all. It's just a matter of knowing what everything in the equation represents. Okay, so here we're given I, we're given the diameter of the copper wire. Okay, it's 2.5 millimeters. And we're given that there's 5.0 times 10 to the 26 free electrons per cubic meter. Okay, so this is going to be N. Okay, and so we have I, we have N. We don't have A, but we can find it because we know that in a wire, it's a cylinder, and so the cross-section is a circle. And so that's pi r squared. So that would be pi times. Now, if the diameter is 2.5, that means the radius would be 1.25. But we need to make sure to convert that to meters because millimeters is 10 to the minus 3. So it should be 1.25 times 10 to the minus 3. That's the radius, and then we need to square that. Okay, so that gives us A. We're looking for V, and then Q, that is the charge of the charge carrier, which here is the electron, which is the elementary charge, which is 1.6 times 10 to the negative 19 coulomb. And so it's a simple matter of basic math to find V. Okay, so V would be I over NA times Q. So I'm just going to quickly do pi times 1.25 times 10 to the negative 3 squared. So the area is 4.9 times 10 to the negative 6 square meters. And then I just need to plug in, solve. Now, something very interesting happens when you actually start plugging these numbers in that I'll show you in just a second. 1.6 times 10 to the negative 19. Okay, so I'm going to do 1.5 divided by, well, 1.5 divided by 5 times 10 to the 26. 4.9 times 10 to the negative 6. And then 1.6 times 10 to the negative 19. I get 0.0038 meters per second, which if I just convert that just for simplicity's sake, that's 3.8 millimeters per second. And so something very unusual about drift velocity is actually very, very small. And so it's a very interesting concept, but when you, for example, turn on a light switch, the light comes on right away. You might think that the electrons are zooming through the wires to go from the light switch to the light, but that's actually not the case. Drift velocity tends to be very, very slow. 3.8 millimeters per second, that's amazingly slow. Okay, and so if you take like a paper clip and you put it on a battery, or you make let's say you make a simple circuit with a battery, the light bulb comes on right away. You might think that because it comes on right away that the electrons are actually moving very quickly. And each individual electron might be moving very quickly, but overall, the drift velocity of the electrons is actually very slow. Okay, the reason the light comes on right away is because if you imagine the wire going from the switch to the light bulb as a giant pipe filled with the electrons, as soon as you turn on the switch, all of the electrons start to move. And so even though they're all moving very slowly, there's already electrons right next to the light bulb ready to turn on immediately the light as soon as they go in. Okay, so drift velocity values tend to be very small. Okay, pause there if you need to look at that some more. Okay, and then this just has the work that we just did. Okay, take a look at this problem right here. It says the diagram shows a wire that has been pinched such that the diameter at x is half the diameter at y. There is a current of I flowing through y, and the drift velocity of the charge carriers at y is v. Which of the following are true of the current and drift velocity at x? This is actually based off of a previous IB question related to drift velocity. Okay, so basically we're asked to compare the drift velocity at x to the drift velocity at y, keeping in mind that the diameter has been cut in half at x. Okay, so what is going to happen? Well, if you use the analogy of water flowing through a pipe to electric circuits, imagine you take a garden hose and there's water coming at the end, and let's say you put your thumb over the end to cover up half of the end. What happens to the water? Okay, well, if you've ever done this with a garden hose, you know that the water is going to come out much faster if you cover up part of the end. Okay, the same thing is going to happen here. The drift velocity at x is going to be much higher than it is at y because the area is much smaller. Okay, now the current is going to be the same at x and y. The amount of charge flowing at x and y per second has to be the same. The reason for that is if that wasn't the case, that means that that charge would be pulling up inside the wire, which doesn't happen. Okay, so the current at x and the current at y have to be the same, because otherwise you would have charge accumulate at points along the wire. Knowing that the current is the same, if you think of the equation I equals NQV, oh, what is it? NQV times A. Okay, this is basically one of those math questions that we've seen before where it says, like, if this happens, what happens to this other thing? So if you know that the I's have to be the same, and you know that N is going to be the same, and Q is going to be the same, then the only thing that changes is V and A. Okay, so how does A change if the diameter is half? Well, A is pi r squared, or pi times d, pi times d over 2 squared. So if you half the diameter, that basically means you're going to decrease the area by a factor of 4. And so in order for I to be the same on both sides, if A goes down by a factor of 4, that means V also has to go up by a factor of 4. And so the drift velocity at x is going to be 4v, but the current at x is going to be the same. Because again, you have to have the same amount of charge flowing per second in the pipe, otherwise the charge would pool up somewhere in the pipe. So the answer to the question is B. Okay, so that's an example of what this type of question looks like on the IB exam. Okay, that question was actually asked a couple of years ago. Okay, so that's actually a pretty recent question. Okay, so now that we've talked about what current is, we've talked about the idea of drift velocity, we can now start talking about the basics of electric circuits. I am going to go ahead and stop this video here, and then we will jump into talking about how circuits work in the next video. As always, please let me know if you have any questions, and I'll see you guys in the next video.